recording here. Oops. Do you wanna... Oh no, just fold it over else. Okay, so make sure you get your assignment 1 in. Let's do now. Right. Looks like I have a good sized pile, so that's good news. Oh, and I guess I should, did anyone not get a term schedule yet? I still have 2 for some reason, so anyways, doesn't matter. So today we'll just keep going in chapter 2. So like I said, if you don't have a copy of these notes, I'll have them up here, but also I can run upstairs and grab you photocopies after class. Okay. I keep not making enough somehow. Okay. So we'll do a review. It's all in the notes, right? We talked about, well, we introduced this new section of probability. I guess I will do a review. Right, so we talked about just what is a random process, right? Something that generates some sort of random outcome, right? And then we talked about the sample space is the list of all possible outcomes. We talked about things being disjoint, right? Meaning they can never happen at the same time. And then how do we calculate probabilities if things aren't disjoint, right? So that's what we were talking about here, where we've got this overlap, right? And then, so that's when we developed this general rule. The probability of A or B is the probability of A plus the probability of B minus that overlap of the probability of A and B. Okay. We talked about probability distributions. Right, so a probability distribution is where we have a list of all the possible outcomes, right, all the disjoint outcomes, and their probabilities below. Then we ended talking about the complement of an event, and we have a pretty good understanding of what the complement of something is. Right? And so it's the opposite, right? So if you roll a die and B is the event 4 or 6, then the complement of B is 1, 2, 3, 5, right? Everything that's not 4 or 6. Same thing if you're talking about genders, right? So male, the complement of being male is female, right? So we don't really need a formula for calculating the probability of the complement of an event A. It's just going to be 1 minus the probability of A. So not that crazy, right? If I told you that the probability of picking a male is 0.7, you know the probability of picking a female is 0.3. So nothing crazy there. Any questions though before we start our new stuff? Oh, okay. So we'll kind of keep going here. Let me just make sure that I'm not on mute. That's happened before. Right, I recorded a whole lecture on mute. I know. So now I'm paranoid. Okay. So independent events, we've already talked about disjoint events, right? They can never happen at the same time. Okay. Independent events are a little bit different, okay? Because two events are independent if knowing the outcome of one has no effect on the probability of the other. Okay? So for example, knowing that you flipped 4 4 tails in a row has no effect on the probability of the tails on your 5th flip, right? So that would be an independent event. A lot of things are not independent. Sometimes we say dependent, but often we just say not independent for some reason. I know it should be dependent, right? But we just say they're not independent. And I don't know why, it's just something I guess I caught myself doing, but I was trained to do it by someone. It's not all my fault. So anyway, so we just say not independent. You could say dependent, it's fine. Some examples, right? Common examples, weather, for example. Snowed today. Congratulations, you made it here. Nice work. All in one piece too, that's good. Right, so it snowed today. The probability of it snowing tomorrow is higher than if it was 30 degrees out, right, and sunny. And so probabilities that depend on some sort of previous outcome, right, or just depends on something else, those are not independent. Right? Stocks, for example, are not independent, right? One stock goes up, the other one might go down or it might go up, right? But it depends on what's happening in the market. Right? Disease, right? Whether it's genetic or someone at the school got what's a common school H1N1. Someone gets it, everyone has it, right? And so there's a huge outbreak, right? So if someone has it at the school, then the probability of you getting it is much higher, for example. So these are all not independent events. Okay? And what we're going to do is we're just going to develop some tools for figuring out if 2 things are independent. Right? And we can use math to do that. I've kind of got it hidden in here. But on your formula sheet, we have if A and B are independent. So this is only true if they're independent, then the probability of A and B will be the probability of A times the probability of B. Okay? That's only true if they're independent. Okay? And so what we're going to do is, if I give you those 3 probabilities, and then I ask you, are A and B independent, right? Then you can do this check, right? You know this number, you'll know this number, and you'll know this number. You can multiply these 2 together. If they're the same as this, they're independent, right? If it's not the same, most likely, then they're not independent. Okay? Whoop. This bouncy chair is wasted on me, or maybe it isn't. It's pretty fun. Anyways, someone else should steal it next class. If A and B are independent, so I'm just going to highlight here. This is on your formula sheet. I'll point it up here. I think it's the last thing. If the probability of A and B is equal to the probability of A times the probability of B, then A and B are independent. Okay. So, of course, if that's not true, then they're not independent. You can move on. So that's how we're going to do it. We haven't really applied any of these concepts quite yet, right? And so let's have a look. I snuck an example in here. Example. I'll call this example 1. So, typical kind of question. In a math class of 30 students, 17 are boys and 13 are girls. Fair enough. On a unit test, 4 boys and 5 girls made an A grade. I don't know why I didn't reword this. I stole it from somewhere and should have reworded it. But anyways, they made an A grade. Congratulations. if a student is chosen at random from a class, what's the probability of choosing a girl, choosing an A student? Right? So we can establish those. And what I want us to do is just start using probability notation, right? Because that's what's on your formula sheet, right? So it might be helpful if we start kind of establishing this notation. How do I insert a page here? I'll go to the bottom. Or can I squeeze it in on here? There's some space after the second example, so I'll just put it on there. I don't know what you guys want to do. So example 1. Okay. First thing I'm going to do is let G be the event of choosing a girl. All right. So G is going to be the event of choosing a girl. Now we can just use G in place of choosing a girl, and then it saves us a lot of writing. Right? And so, and A, I'll let A be choosing an A student. So we want to know what are the probabilities of, what's the probability of G? The probability of G, if there's, oh, I don't have to scroll, we've got it in front. I think there's 13 girls, right? So in a class out of 30, there's 13 girls. So the probability of choosing a girl is just 13 out of 30. If you have a look at assignment 2, right, I've just given you the probabilities, right? So you don't have to read the blurb and try to figure out what the probabilities are. I just give them to you, right? But it's good to see where they came from. Or we could say 0.43 repeating. You could round if you wanted to. Right, so it's just, do you like working with fractions? I don't. So I would just convert it to a decimal. You lose a little bit of accuracy, but it's okay. The probability of choosing an A student, well, there were how many? I think there were 5 girls and 4 boys that got an A. So in total, there's 9 out of 30 students who got an A. So 9 out of 30, or just 0.3 if you want. Two. Draw a Venn diagram of the 2 outcomes. How am I supposed to do that? We haven't even talked about Venn diagrams. I know, but I think you know what they are, sort of. Might have seen them. They're pretty good for jokes. So a Venn diagram starts with a box. That's the sample space. And so all possible outcomes have to be contained in this box. And then we have 2 outcomes that we're interested in. So we draw 2 circles. 1 circle for a G and 1 circle for A. And then this overlap, right? This overlap here is the girls that got an A. Outside here, so in this circle, you have all your girls. Right? So outside this circle, you have all your boys. In this circle here, you've got all your A students. And so in this half moon area, you've got your A students that are boys, right? And then out here, you've got all your, well, they can't be A students, so they're not A students, and they also can't be girls, right? So it's all the boys who didn't get A's. So what we can do is we can just label each of these parts, and that'll help us answer some questions, right? Or could. So in terms of this kind of half moon G, right? Because I'm talking about each of the parts individually. We know there's 13 girls, right? But it might be more helpful if we start in the middle here and kind of work our way out. And that's in general for Venn diagrams, if you're drawing them, it's good to start in the middle, right? Figure out all the overlap, and then you can kind of blossom out to figure out the rest of the probabilities. Okay. So let's start there. So we had 5 girls that got an A, right? So this overlap is 5 out of 30. We just figured out, so we know there's 13 girls, right? But then 5 of those have already been accounted for in the overlap, right? And so we have 8 plus 5 is 13. Right? So 8 out of 30 girls that didn't get an A. Can do the same thing for the A students. Right? We know there's 9 A students. 5 of them are girls. We also know that there's 4 boys who got an A, so this must be 4 out of 30. And then finally, we can do this area here. We decided that this area, well, it can't be the girls, so it has to be boys, right? And it also can't be a boy that got an A on the test, right? And so we have 13 boys left over, right? Because there were 17 and 4 of them got an A, so 13 left over. So now we could answer all kinds of questions. For example, what's the probability of choosing a student that is male who didn't get an A? Right? We've identified all these areas. Right? One thing to keep in mind, because remember, this is the sample space. Right? And so all of these probabilities have to add to 1 still. Right? So if you're doing this, you can just check to make sure that all your areas add to 1. If they do, you did it. Okay. So there's your Venn diagram. We want to know what's the probability of choosing a girl who got an A on the test. Right. So in terms of probability notation, the probability of choosing a girl who also got an A on the test, so that's the probability of G and A. There's lots of ways that you could find this probability, but I'd say the easiest way is just to look at your Venn diagram that you just made. And so, and I think I have that, yeah, so on assignment 2, question 1B, use a Venn diagram to find the probability of seeing a whale but not a dolphin. And so you're just going to draw your Venn diagram and use that. So I'm not expecting to see any calculations or anything. Just draw it out and figure it out. So the probability of a girl and an A is, we already found it in our Venn diagram, 5/30. Or if you prefer decimals, 0.16 repeating. How about 4? Choosing a girl or an A student. 2 ways that we could do this. We're going to use the formula, but another way that you could do it is just say, well, so I want to pick a girl, so I have to be in that circle. So I need to be in that circle most, or an A student, which extends me out to that circle, right? So I don't care which one, as long as it's one of those 2, right? So I'm kind of inside this bubble. Right? And so you could add up those 3 probabilities, right? Or just use the formula, which I think is easiest, but what do I know? So we want to find the probability of G or A, which from our formula sheet, right, is the probability of G. So now I'm just rewriting this because we've got the probability of A or B in general, right? But you want to kind of swap out your A's for G's and your B's for A's. Weird, right? So that could take a little bit of focus. Probability of A minus the probability of G and A. So the probability of G, we said, was 13 over 30. Thanks. The probability of A, 9 over 30. And if you don't want to deal with fractions, that's fine. You could use the decimals. Minus the probability of G and A. Notice that I just made you calculate that in the previous question. Right. So often I'll kind of walk you through a question without telling you, I guess. So this was 5 over 30. So this makes 17 over 30 or 0.56 repeating. That bar had a bit of an accent to it. There. Oh. Right. Notice that all we did, right, was we essentially added up those areas. Right. Here, what we're doing, a little bit different, right? So we could have added these up individually, or we could have said, well, the G circle has 13 and the A circle has 9, and then I'm going to subtract the overlap of 5 ones. Right. So back to that same idea that we had with the deck of cards. Any questions so far? Okay. So 5. Where do I have it? Are choosing a girl and choosing an A student independent? And so here, we have to check if they're independent. So we know from our formula sheet that if G and A are independent, then we know that the probability of G and A must be the same as the probability of G times the probability of A. Because we know these, I'll use the fractions, but you would find the same thing. I'll check the decimals too. So 5 over 3, is that the same as, or sorry, 5 over 30, is that the same as 13 over 30 times 9 over 30? 5 over 30 is 0.166 repeating. Does it equal 117 over 900? I'll put a little question mark up there just to indicate that, oh, I actually am not sure. Converting 117 over 900 to a decimal, we get 0.16 repeating is not equal to 0.13. Right. They would have to be exactly equal to be independent. Okay. So here would have to be exactly equal, right? Unless you've rounded your answers, then you might have to go back and check without the rounding to be independent. So therefore, G and A are not independent. So part C on question 1 for your assignment 2, are seeing a whale and seeing a dolphin independent events? Justify your answer mathematically. I'm expecting to see something like that. Example 2. I actually want you to cut the first question there. I'll put this way at the end here. Let's start a new sheet. Pardon? Assignment 2. There you go. If you didn't get assignment 2, you can grab one after class or yeah. I just have to make myself some more room here. Copy these over. So like I said, I don't want us to draw a Venn diagram. I did that before looking at the question too carefully. I'll talk about why we don't draw a Venn diagram. But just as another example, just to give us an idea of what's going on here. So on New Year's Eve, the probability of a person having a car accident is 0.09. Right, so here I'm just giving you this probability so we can use it, right? We don't have to deal with fractions, so that's nice. The probability of a person driving while intoxicated is 0.32. Yikes. And the probability of a person having a car accident while intoxicated is 0.15. The reason I'm not drawing a Venn diagram is because they're not happening kind of side by side. The 0.15 is actually, if you're driving intoxicated, then you have an accident with a probability of 0.15. So that's why we can't draw a Venn diagram. They have to be on the same level. Anyways, I wouldn't ask you to do it. I just got carried away when I was copying and pasting. So first thing we're going to do is we're going to list these probabilities using probability notation. So 1, 2. First thing we're going to do is just establish some shorthand. Right? If you're going to use shorthand, you should tell me what you're saying is what, right? And so we say something like, I don't know, what are we talking about here? Having an accident and driving while intoxicated. So let A be having a car accident. And I'll let I be driving while intoxicated. And we're given three probabilities, right? First, we're told that the probability of A is 0.09. And we're told that the probability of I is 0.32. And then we're also told that the probability of A and I is 0.15. So there's our three probabilities that we've been given with probability notation. So what's the next thing we have to answer? Are having a car accident and driving while intoxicated disjoint events? Disjoint means they can never happen at the same time, right? We could argue that no, they're not disjoint, right? Because you can drive while intoxicated and have an accident at the same time. Or kind of more powerful would be the argument that no, they're not disjoint because the probability of them happening at the same time is 0.15, right? If they were disjoint, that probability would have to be 0, right? They can't happen at the same time. Here, yes, they can happen at the same time. So 3. Since the probability of A and I is 0.15, which is not 0, these events are not disjoint. These events are not disjoint. And that's all you need to say, really, right? You could go ahead and argue why they're not disjoint, but just saying, well, because the probability of A and I is not 0, there you have it. They can happen at the same time. So 4. What is the probability of a person driving while intoxicated or having a car accident? So we want the probability of A or I. I or A is the same thing. Here we can use our formula. So like I said, with this formula, I'll give you 3 pieces of the information, right? And you have to solve for the 4th. So the probability of A plus the probability of I minus the probability of A and I. So we want to know the probability of A or I. When the probability of A is 0.09, probability of I is 0.32 minus 0.15. This makes 0.26. Are having a car accident and driving while intoxicated independent events? We know how to deal with this now, right? And so we want to know, or we can say, if A and I are independent, then we'll be able to show that the probability of A and I is the same as the probability of A times the probability of I. We have all these 3 pieces, and so the probability of A and I is 0.15. Does it equal 0.09 times 0.32? 0.09 times 0.32 is 0.0288, which is not the same as 0.15. So A and I are not independent. So I'll justify it here. So since the probability of A and I does not equal the probability of A times the probability of I, we can say A and I are not independent events. Any questions about that? One little note that I want to make is that disjoint, right? So what's the difference between being disjoint and being independent? Disjoint is referring to the actual outcomes, right? Can they happen at the same time? Independence is talking about the probabilities, right? Do the probabilities care about each other? Right? And so we're talking about the outcomes versus the probabilities. Okay. So just as a note, disjoint, refers to the actual outcomes, while independence refers to the probabilities. So we kind of have to keep that in mind, because I know those can get boggled.
The PNI equal PA times PI, is that solely used as a check, or can it, so it cannot be used for calculating? Like, say you have PA and PNI, what is PI?
Yeah.
Is there an instance where you use that to get a result?
If I told you that they are independent, right? So if you're told that these two things are independent, then you can use it. Excellent segue to conditional probabilities. So, right, as you can tell, right, we usually want to know what the probability of A and B is, right? So we need some sort of formula that we can always use to calculate them, right? Not just if they're independent. Okay. So 2.2, I'll take you back to the notes here, is on conditional probabilities. So we've already seen a table like this. It wasn't laid out nicely like this, right? But we've seen a contingency table of two categorical variables, right? And so the thing is that even without knowing what's going on here, right, college and degree might not be independent events. And so in this example, they did a survey of 792 teens where they asked, okay, are you going to college right away, or are you going to take a year off, right? Or maybe not going to college at all. And they also asked, does at least one of your parents have a degree already? Right? And so we've got this college variable and a degree variable. And so the college is going to be a C if the high school student is saying, yeah, I'm going to college right away, right, great. Or the complement of C if they're saying, no, I'm going to take a year off, or no, I'm not going to college at all, right? And then you get a D, right, if at least one of your parents has a degree. And then the complement of that would be neither of your parents have a degree. We've got the totals in the margins. So if we let D be at least one parent has a college degree and C, the team went to college immediately after high school, we can answer a lot of questions just looking at this table. And so here, what proportion of teens have at least one parent with a college degree? So remember, everyone in our sample here, 792 is a teen. So we're just talking about out of the whole sample, which one, how many D's are there? And so what you can do is you can say, well, I don't care about if the student's going to college or not, right? Not yet. I'm just looking at how many D's are there? 231 plus 49, and then the total 280. And so the probability of picking a student where at least one of their parents has a degree would be 280 over 792. So you can look at the table and kind of suss out the information that you need. So I'll just put it here, I guess. What proportion of teens? Did I make any other notes? No, I didn't. Great. P of D, right? Because we don't care about where the student's going after high school. 280 over 792. Or 0.3535 repeating if you wanted to. Maybe I'll put these, just copy this. Gets annoying, but more room. (2.2) example 1. I'll just rewrite it here. P of D is 280 over 792, or 0.3535 repeating. Going back, call this example 1. Given at least one parent completed a college degree, what is the probability that the teen went to college right after high school? So now we're saying out of those whose parents at least have one degree, right? So out of these 280, how many, now I've forgotten, how many went to college right away? What's the probability that the teen went to college right after high school? So out of these ones, 280, 231 went to college right away. So the probability of the teen going to college right after high school, given that the parent has a degree, or at least one parent has a degree, is 231 out of 280. So the probability of C given D is 231 out of 280. or if you prefer, 0.825. This here, this given, is a conditional probability. Right? So C given D narrows down your pool, right? Because now you're saying only out of these 280, right? You don't care about anyone else. Just out of these 280, now what's the probability of the teen going to college? Right away. So here we have another given. So given that a teen is randomly selected and she did not attend college right after high school, okay, so that's the information that we have. So now you have to zoom in on everyone who didn't go to college right away. Right, so that's the complement of C. What's the probability that at least one of the parents has a college degree? So now we want to zoom in on everyone here, right, who didn't go to college right away, and the proportion of parents who have a degree, 49 out of 347. Denoting this, right, now we have to incorporate our complements in there, right? So we've got the probability of a degree given that they didn't go to college right away, right? The complement of C is 49 out of 347. Or as a decimal point, 141210375. Excessive. Okay. So now we have these probabilities, right? So now we've looked at, okay, well, if we're looking at these conditional probabilities, right, then we zoom in to one marginal value. So these are called your marginal values, right? They're in the margin. We'll have a look at a table where we've converted all these numbers to probabilities, right? And then those would be marginal probabilities. But of course, there's a formula for this, right? Because tables aren't always going to be nice to look at like that. And so these conditional probabilities, we can use the formula, the probability of A given, so this vertical line is given, B, is the probability of A and B over the probability of B. Just make a note here. This is given. We love that shorthand notation. Condense it all. Okay. So if I asked you, let's have a look at, the one we just did. We were looking at the probability of D given, not C, right? Complement of C. So if we're looking at the probability of D given, not C, I almost put a prime on there. I made a note in my notes. Sometimes I do C prime, and that's the complement still. Right. I'll try to use the C because it's what's on your formula sheet, but for me, when I do my work, I just do primes, but I'm trying. Okay. So what we said, our answer, right, when we had to look this just at the table, we said, well, that's going to be 49 out of 347. if we apply the formula, the probability of D given not C, that's the probability of D and not C over the probability of not C. Probabilities, I'll just skip one thing, right? Because these are all divided by 792, right? If we're looking at the probability of D and not C, right? So we have to be in the degree column and we have to be in the not C. So that's going to be 49 out of 792. But those 792s will cancel because they'll be in both the numerator and the denominator. So I'm just going to ignore them. Right? So that's how we get this 49. And the probability of not C, right? So then we don't care what's going on with their parents, right? That's the 347 out of 792, but again, it would just cancel, right? So that's how we get 49 out of 347.
Between the D and the C, that's a division.
You mean this one?
Yeah.
Yeah, so the vertical line is given. Yeah. I want to make a note of that. And so that's the one on your formula sheet. Probability of A given B is the probability of A and B over just the probability of B. Just complete my thought here. It'd be 49 out of 792 over 347 out of 792, which is the same as 49 out of 347. So you get the same thing, right? Now, if you want to use the table and only use the table, fine by me, right? But you have the formula and they do the same thing. So, any questions about that? Okay. Great. So in terms of terminology here, you've got your marginal probabilities, right, in the margins, and here you've got your joint probabilities. Let's have a look at, I converted this table to just probabilities. And so now, have a look here. These probabilities here are marginal probabilities. And these probabilities here in the center are joint probabilities, right? Because they're shared between the two events. So joint probabilities. Guess I crossed some stuff out. Try to do it better. There. So again, if we had to find using, so find the probability of C given D, just using the original table, C given D, so now we know, okay, well, we have to be in the D column. Where was it here? We have to be in the D column. What's the probability of C? That's the 231 over 280. So we could use that, or we could use our probability notation, right? So here, the probability of C given D, we can rewrite as the probability of C and D over the probability of D. The probability of C and D from this table here, it's a little bit easier to see, right? Because now we have to be in the C row and we have to be in the D column. So this would be the probability of C and D, 0.29. divided by the probability of D. The probability of D is 0.35. So what you would end up with is 0.29 over 0.35. 0.829. Notice that there's a slight difference. The problem is that I'm using rounded probabilities in here, so it will affect your answer slightly. I would accept either way, right? If you show me that this is how you found it, great. That's the answer I'm expecting. If this is how you found it, great. That's the answer that I'm expecting. As long as you show your work, you won't lose that many marks, right? Even if you use the wrong values or for whatever reason, I'm looking for process, right? So as long as you've got the idea of it, then that's good. So we'll do an example. First, let's talk about tree diagrams, and then I'll get you to do one. So we usually have to talk about consecutive events, right? So on day 1, this happened. On day 2, this happened. If you've had a peek at your assignment 2, that sounds kind of familiar to question 2. Right? You go on a whale watching cruise on 2 consecutive days. And so here, right, we've got day 1, day 2, right? Person 1, person 2. Card 1 that you pick up, card 2 that you pick up, right? So these are consecutive events, and you can do a long list of them if you wanted to, but what you'll find is that it's easiest to visualize these things with tree diagrams. And as soon as you have more than 2 layers, it gets a little out of hand, right? Because if you imagine a tree diagram, right, you've got 2 outcomes, right? Yes and no, and then each of those has 2 outcomes. But what if you had 3 outcomes? Each of those has another 3 outcomes, 3 outcomes, 3 outcomes, right? So it gets out of hand pretty quickly. I'll stick to 2 and 2. Nice and neat. Mostly because I can't fit it all on a page if I try to go more than just 2. So, for example, 13% of students earned an A on the midterm. Right? So you write a midterm, then you write a final. Right? Those are consecutive events, which we're going to display as layers in our tree diagram. So we've got a midterm event, right? And then they write the final. So of those students, 47% got an A on the final. Great. Right? So we've got the midterm, we've got the final. 11% did not get an A on the midterm, but got an A on the final. Right, so now we have to kind of map this out, and like I said, we're going to use a tree diagram. What you'll find is the tree diagram is going to be all of the work, essentially. Once we have it built, we can answer pretty well all of the questions that we need. Right? Yeah.
Are you saying that 47% of the 13% or 40%?
Yeah.
Okay.
So, and that's the thing, right? So that's why we have to map these out, because we have this conditional probability that if you got an A on the midterm, then the probability you got an A on the final is 47%. Right? So we've got this given situation. Okay. So do I have room on here? Now it gives me space? Great. All right. Sure, why not? So what we're gonna do, oops. I'll just make this example too. For 2.2. First thing I'm gonna do is I'm gonna develop some shorthand, right? Just so I'm not always writing out all these words. So I'm gonna let M be an A on the midterm I'm not going to use A, right? Because we're talking in terms of A on the midterm, A on the final. So I need to kind of keep those separate, right? And so let M be an A on the midterm. And then let F, ironically, be an A on the final. So if we have to draw a tree diagram, we haven't seen an example, but here it is in the example. Okay. First thing I'm going to do is I'm just going to draw out, right? We know, so the midterm can go one of two ways. Either you got an A or you didn't. And then you write your final. So again, depending on which branch you went down for the midterm, right? You could still get an A on the final, even if you didn't get an A on the midterm. So what I'm going to call this, I'll call this the midterm layer. And this is the final layer. Because I know you'll have questions for the assignments that you're doing. And so when I say layer, I mean, here's your first layer, here's your second layer. Because you'll have a day 1, day 2 layer, right? So we can map out all the outcomes first, right? So first, establish how many kind of branches you have at each layer, right? And then draw those out. And then we can just add on. So either you got an A on the midterm or you didn't. And then each of these, either you got an A on the final or you didn't. A on the final or you didn't. And then we're told that 13% of students got an A on the midterm. So the probability of going down this branch, I'm converting my probabilities to decimals, right? Because when we use them in our calculations, we should have our decimal versions, right? 0.13, making the probability of not getting an A on the midterm 0.87, right? The complement. Let's, and then we had the sneaky statement of those students who got an A on the midterm, 47% got an A on the final. And so now we know that if we've headed down this branch, then the probability of F is 0.47. So now we have these conditional probabilities. So 0.47. Making the complement 0.53. Same idea. 11% did not get an A on the midterm, but got an A on the final. And so they didn't get an A on the midterm, but got an A on the final. So this branch is 0.11. So the complement is 0.89. So we're not quite done. What I want to see, right, is, so build a tree diagram labeling all the appropriate probabilities. What we're usually interested in is the probabilities at the end of each branch, right? What's the probability of getting an A on the midterm but not on the final? What's the probability of not getting an A on the midterm and not getting an A on the final? And so what we do is, I'll show you technically what we do. But to find the probabilities at the end of each branch, you just multiply down. Right, so it's this times this. This times this. This times this. This times this. And so how I'm going to denote these is I'll write that here, this outcome is MF, or M and F. At the end of this branch, I've got M and the complement of F. Here I've got the complement of M, F, and the complement of M, the complement of F. I've cut out the and, because they just have to happen consecutively. So what we can do, just to show, is that here the probability of M and F is the probability of MF, just to show. Is the probability of F given M times the probability of M. I didn't spend a lot of time on it, right? But I introduced that formula here. Right. Forgot to mention that actually. The probability of A and B, right? That's from here. We can rearrange this conditional probability formula for the probability of A and B by multiplying both sides by the probability of B, moving that over here. And so yeah, the probability of A and B is the probability of A given B times the probability of B. So this is the formula I should have made a bigger deal about, but that's the formula that you use in general. If A and B are independent, then the probability of A given B is just going to be the probability of A, because it doesn't care what B is. So that's the formula that I'm using down here. So the probability of F given M times the probability of M. But what I'm going to show you is that really we're just going to end up multiplying down the branches. So you don't need to know this formula necessarily. You need to have seen it, be aware of it. But practically, we just do 0.47 times 0.13. Because the probability of F given M is just this probability. Probability of F given that we went down this branch. Which is going to be 0.0611. Or just multiply down each branch to find the probabilities. So the probability of M and the complement of F, that's our next branch, right? M is 0.3, the complement of F is 0.53, is 0.13 times 0.53, 0.0689. Probability of not M and F, 0.87 times 0.11. Which is 0.0957. And the probability of not M, not F is 0.87 times 0.89. 0.7743. So we can jot these down. 0.0689, 0.0957, just so they're all in the same place, 0.7743. And of course, 0.0611. These are all the possible outcomes, right? You either got an A on the midterm or you didn't. You got an A on the final or you didn't. Right? And so one thing that you want to check is that if you add all these up, that's the entire sample space, right? So the total has to be 1. So the total must be 1. So we'll finish this off next day, but what you'll see, so just looking at question 2, what's the probability of a student earning an A on both the midterm and the final? Now you can just look at the probabilities that you found, right? That's the probability of M and F, 0.061, right? So then you can just write down that number. Okay? So try those and we'll finish it off next day. And I'll see you, on here. Yeah. See you guys on Monday, I guess. Weird. Have a good weekend. Bet. Oh yeah, if you didn't get an assignment, come grab it. I do. There you go. No worries. Of course. Assignment?
I went to a library, but I couldn't find the one that like, can I get from there?
Yeah, you bet.
I see an assignment.
You
And
got it.
One of these two.
You got it.
Do you have it printed out?
Chapter 2. I'm gonna run upstairs and grab photocopies right now.
All right.
Yeah. So if you want to come with,
Yeah, I will.
you can have one.
Chapter 2, you posted that on Moodle, right?
Yeah. But if you want me to get